This talk is going to focus on what the volatiles do after they leave the magma and how subvolcanic volatiles may play a role in the phreatic part of volcanic unrest. I'll start out just showing you the texture. Then I'm going to give you some background, and then I'll get back to describing the rocks and pondering their significance. You're looking at a backscatter image of what appears to be a feldspar crystal, but the parent crystal is actually amorphous silica, or opal A if you will. And it shouldn't be stable at magmatic temperatures. It's encased in fresh pumiceous glass, and it includes glass as well. Also note that the white crystals are fresh orthopyroxene, and we'll get back to that. Now I'm going to force you to listen to some background material. Phreatic and phreatomatic eruptions are notorious for having few precursors. They're hard to predict, and we're not sure of why they even occur. Are there some subsurfaces that are better suited to creating phreatic eruptions? Many phreatic events seem to be triggered by magma. How quickly can we unsettle the hydrothermal environment and trigger it into eruption? Another thing to keep in mind is that many volcanoes are underlain by intensely altered material. That's because continual degassing of SO2 and condensation of magmatic steam in the shallow subsurface makes for a highly acid-toxic brew. We get advanced argillic alteration, or the more extreme vuggy quartz or residual silica. As magmatic vapor condenses, it cools and it becomes increasingly acid. The acid will typically leach shallow volcanic rocks until all that's left is opal and silica. Less extreme versions of this alteration are quartz alunite or quartz kaolinite lithologies. This general environment is important because it represents the lithocap that overlies porphyry ore deposits, and it also hosts high sulfidation epithermal gold mineralization. The opal itself looks something like this. It forms as nanoparticles and can unmix either through neutral fluids or the acid fluids we've been talking about. It starts out very hydrous and gel-like, as shown on the right, but with time it can dry out and form various forms of crystalline silica, opal CT, or even ultimately quartz. Turns out that opal is frequently erupted out of volcanoes during phreatic activity. It's happened at Ruapehu, Tongariro, Papandayan, and Ontake in recent years. About a year ago at Cotopaxi, juvenile glass was found in contact with opal-replaced phenocrysts, or in other words, opal pseudomorphs. These images from the recent paper by Gaunt and others show the products of phreatic eruptions, where the unrest did not or has not yet led to a purely magmatic eruption. Plausibly, the phreatic debris could represent old pumice fragments infiltrated by acid, where the glass was non-reactive, but the phenocrysts were attacked and replaced. Alternatively, as favored by the authors, this could represent fresh andesite melt that is quenched against hydrothermal minerals during subvolcanic intrusion and ultimately explosion. We're going to show you a more extreme example of this kind of association of glass and opal at Kawah Ijen in East Java. The volcano crater here is filled with the largest acid lake in the world, with a pH around 0. The water is over 10% dissolved solids, primarily sulfuric acid, but with healthy amounts of HCl, HF, and trace metals. Sulfur mats float on the top. Co-authors Vincent van Hinsberg and Kim Berlo have worked for years at Ijen and wrote several papers on acid alteration, which includes abundant opal-replaced phenocrysts. In the photos to the left, you can see tabular phenocrysts that are now 100% hydrous amorphous silica, surrounded by a hydrous silica ground mass. Textures imply that glass is altered first, followed by olivines, pyroxenes, and calcium-rich plage. On the right is a vug filled with opal and silica, and you can note the colloidal particles in the center. Variations in backscatter intensity apparently represent variations in density or water concentration in the silica. In 1817, eruptions through the lake hurled hydrothermal debris and fresh pumice out onto the surface. The explosions lasted for weeks and sent floods down several of the local valleys. Dry ash and pumice landed on the nearby coastal city of Banyuwangi. It doesn't appear that the lake was entirely emptied, but it was radically changed, and pumiceous muddy deposits were emplaced all around the crater, where they can easily be found today. Lahar deposits contain large, frothy pumice lumps of low silica dacite. We've sampled pumice from a variety of locations around Ijen, some areas on the volcano flanks, which are very unlikely to have seen any significant amount of acidic fluid in the past 200 years. Bits of opal and debris are found in the lahar deposits. For example, the left image is entirely amorphous silica. It may have started out as kaolinite, but is now 95% opal with a bit of adhering alunites on the edge. To the right is a piece of opal and debris found within the 1817 pumice itself. You can see the pumiceous glass matrix all around it. You can also see that the layering of colloidal silica is not concentric, as it would be if this were a vug that were being filled post-eruption. Out here you'll notice an opal-replaced phenocryst. In fact, almost all the phenocrysts seen in this image are made of opal. Here is an example in reflected light. It's the greasy gray material and it does not polish well. Here's the same image in transmitted light. The sample was impregnated with epoxy, which is blue. You can see bits of remnant feldspar in white and brown glass. When we cross the polars, the opal goes dark. It's isotropic because it's amorphous. The feldspar displays its characteristic polysynthetic twinning. And we've done separates of these silica-replaced phenocrysts and have XRD and TCEA data. We've done in situ FTIR, electron microprobe, and laser ICP-MS. And the opal is almost entirely silica and water with only trace amounts of alumina, titania, etc. The surrounding glass is pretty normal dacite in composition, and there are minimal, if any, differences between these so-called inclusions and the adhering matrix glass. A few more images to observe. Toward the bottom is a wholly replaced, relatively homogeneous feldspar. Toward the top is a replaced pyroxene. The pyroxene is replaced by sheets of opal that cross-cut the original pyroxene layering. The sheets are infilled by the epoxy during impregnation. Around both pseudomorphs, you'll notice the sharp boundary between the glass and opal. Our analyses by a variety of techniques indicate that the opal contains 2 to 4% water, which is less than what one might expect for an initial amorphous silica alteration, hinting at the possibility that the opals are partially dehydrated. Indeed, the very low delta D of the opal-replaced phenocrysts, shown in green, well below -100, and their very high oxygen 18 contents between +12 and +25, is consistent with formation of the opal at hydrothermal temperatures and some subsequent dehydration. So there are some important observations to consider. The glass is always fresh and microlite poor. There are fresh phenocrysts and opal-replaced phenocrysts, as well as some phenocrysts that are partly replaced. The vesicles show minimal evidence for infilling with secondary minerals. So one possibility is that the pumice was altered after eruption at the surface of Ijen between 1817 and now. There is some experimental evidence that glass can be less reactive than crystals, though that doesn't appear to be the case in the altered rocks at Ijen. More to the point, we find these textures at multiple sites on the volcano, including areas where acid fluids aren't likely to have been present, and we'd expect to see opaline material in the vesicles if fluid were migrating through the deposits after the eruption. So we don't really favor this hypothesis. Our favorite explanation is that fresh magma, including fresh phenocrysts, infiltrated the opal-altered materials under the volcano hours or even minutes before eruption. There's only little time available because opal isn't stable at high temperature. And we verified that through a series of experiments by co-author Kayla Iacovino at a variety of temperatures, pressures, and added water. All experiments were done in cold seal vessels for 24 hours. In all experiments, the glass started to grow microlites and the opal started to break down. There's fresh opal A in part A, and then in part B, C, and D, you can see that the opal is starting to get cooked and becomes vesicular and is starting to break down. And in all cases, the glass has started to form microlites. As mentioned earlier, we did analyze the samples for water by a variety of techniques. On the left, you can see in this FTIR map that the opaline particles are hydrous, so that water is abundant at 1630 inverse centimeters. We also heated up the pumice fragment for 30 minutes at 1 bar in a fluid inclusion stage, conditions maximizing diffusive loss. After 30 minutes, we lost 90% of the water in the sample, and all the remaining water was consistent with structural hydroxyl, as might be found in quartz. So clearly, the opal has to be incorporated into the pumice within hours at most to preserve some water in the opal, and keep it amorphous. Besides the rapid timescale, there are two other kind of mind-numbing aspects to this phenomenon. One is that the assimilating melt can so quickly infiltrate all the vugs in the rocks and the pores and pockets in the pseudomorphs, creating the fresh glass as apparent inclusions in the opal. It's also hard to understand the setting of the pseudomorphs prior to eruption. Were they set within an opaline ground mass? Were they loose sediments beneath the lake? Were they floating in liquid sulfur? How did they get incorporated into the infiltrating melt? I don't think we know the answer fully to that yet. Before I finish, let's step back for a minute and ignore the Ijen example, but consider the more common incidents of acid-altered materials in phreatic eruptions. What happens when you heat up hydrous alunite, opal, or kaolinite, all of which contain more than 10% water? Could we get phreatic explosions even if there weren't abundant aqueous fluids around, simply by generating steam from hydrous minerals? Or if the opal is impeding permeability, can heating it cause it to break down and thus rupture a seal? How close does the magma need to get to this hydrous rock to induce explosions or eruptions? And if we look at more phreatic eruption debris, are we going to find more of these sorts of materials? I'm not sure the answers to all these questions, but I'm keen to find out, and I hope you are too.